Hello. In this example, I'm going to tell you how to test for symmetry with respect to the x-axis, y-axis, and origin for any given equation. Now this works whether it's a function or not. That's important to remember. Let's start out with the x-axis. For x-axis symmetry, helps if I can spell this correctly. For x-axis symmetry, here's what you do. You replace the y value with negative y. Then you simplify. If it then looks like the original equation, it is symmetric with respect to the x-axis. Now I'm going to use this abbreviation WRT, that means with respect to. Okay, that is x-axis symmetry. Now let's talk about y-axis symmetry. Y-axis symmetry is pretty much the exact same thing, but instead you're going to replace x with negative x. Then you're going to simplify again. If it's the same, again, it is symmetric with respect to the y-axis. Okay, next I'm going to do origin symmetry. Now for origin symmetry, what you need to do is you need to replace both x and y with negative x and negative y. Then, of course, you're going to simplify. And if it's the same, it is symmetric with respect to the origin. Okay, let's talk about this for just a second. I'm going to do a small little XY plane here. If this is the XY plane, a function that is symmetric with respect to the x-axis would look something like this. In other words, if you flipped this across the x-axis, whatever's up here would go down there and vice versa. Therefore, it's symmetric with respect to the x-axis. Let's look at symmetric with respect to the y-axis. That would look something like this. If you flip it across the y-axis, this point over here becomes this point over here. Now, this is what you should see. For the x-axis, this y goes to the opposite sign. That's why I can replace the y with negative y. And whenever I simplify, I still get that original function. The same thing with the y-axis symmetry along this. If this x here goes to the other side, it's an opposite sign. That's why I can replace x with negative x. And that's why whenever you simplify it, it remains the same equation. Now, origin symmetry can be a little bit tricky sometimes. Origin symmetry can look something like this. It can look like this, or it can look like a circle centered at the origin, or other types of figures. Basically, for this one way to tell is if you flip this entire thing upside down, it's still going to look the same. In other words, if I have the cubic function and I flip it upside down, the cubic function is going to look like this, which is the same as the original. Or if I had a circle, if I flip it upside down, it's the same as the original. Now, another way to see that is this quadrant here should be a reflection of this quadrant here about that line right there. And the same thing, this quadrant here should be the same as this quadrant here, but it's a reflection about that line right there. So that's another way that you can see by not picking up the paper and turning it upside down. So there you go. That's how you can test for origin, x-axis, and y-axis symmetry. Now, one thing I need to emphasize, although origin symmetry can have both functions and non-functions, and the same thing for y-axis symmetry, x-axis is a little bit different. That's this blue one right here. X-axis symmetry can never happen for a function. So functions are not allowed for this. The reason it's not allowed is because for a function, if there's a point here, there cannot be a point down here. Therefore, every x-axis symmetry equation that you have, there will be 2 points on top of another, which means that it is not a function. There's actually one, but it's just the equation y equals 0, which is the x-axis. And that's the only time that happens.